So this Griffths capsule, we often come across it during our bachelor's and even in class 11th and 12th. So this question goes as such. For example, sir, if we have a huge sphere, say for example we have Earth is a huge sphere. If somehow we manage to dig a tunnel through Earth, let's say through its diametrically opposite ends, and I happen to drop a solid ball of some mass m through the tunnel.
Okay.
So how is this particle going to behave? So is it by any chance possible that this particle, once it is dropped from one of the poles, it goes to some other diametrically opposite point? Is it by any chance possible that this particle executes simple harmonic motion? And if it does, so can we calculate its time period?
Absolutely, absolutely. This is one beautiful problem in physics. Okay. Now, what the Mohsin sir is doing is that he has dug the tunnel from the North Pole to the South Pole, so he has made my job easier. And next, what he has done is that he has taken a particle and dropped it from the North Pole. So obviously, there is what we call as gravitational force. And because of the gravitational force, what will happen to this particle is that it will tend to move towards the center. And the moment it reaches the center, the net force on this particle is equal to 0. But don't get confused that at the center of the Earth it will stop. It is not going to stop.
No, because of inertia
motion. It will have some momentum. Because of that momentum, it is going to overshoot its main position.
Okay.
And guess what? It will move towards the South Pole. But when it moves towards the South Pole, now the gravitational force will be directed towards the center of the Earth like this. And as a result of which, what will happen is that this particle is going to execute simple harmonic motion from North Pole to South Pole and then back.
Okay, sir.
Okay.
So now since it's established that the motion will be simple harmonic, so can we somehow calculate the time period of this simple harmonic motion?
Obviously, we can calculate. We can easily calculate.
Can we give it a mathematical touch?
We can do that.
Please do it. Please do it for us, sir.
We can do that. Obviously, we can do that. The first and foremost thing you must know is that what is the acceleration due to gravity on the surface of Earth? And obviously that is g, isn't it? What about acceleration due to gravity at the center of Earth?
It is 0.
That is 0. Absolutely. Okay. Now, if we go from the center to the surface, question is like this: if we go from center to surface, what will happen to acceleration due to gravity?
It will obviously increase,
isn't it? And it increases linearly. So what I'm going to write is this. I'll write an equation like this: g inside. This is the acceleration due to gravity inside. That will be equal to g into x divided by r. All right. While r is the radius of Earth, you can say that this is the radius of Earth, which is equal to r, and x is any distance from the center. All right. So acceleration due to gravity at this very point, which is g inside, will be this. All right.
So if I may stop you.
Okay.
Once we calculate this acceleration due to gravity, since it's a function of the depth, so you are telling me that from this expression, this acceleration due to gravity at this point is actually a function of this distance x.
Exactly. Okay. Now see that what we want is available, and that is this acceleration due to gravity is a linear function of displacement.
Okay.
And the situation is inviting a simple harmonic motion, isn't it? What I'm going to write is this: the generalized equation for the linear SHM. Acceleration of a particle executing linear SHM is this: omega square multiplied x. The problem is done and dusted. Okay? X and x is going to cancel. We are left with omega. So what omega will be? It will be equal to root of g divided by r, isn't it? Okay. Easily we can calculate the time period. The time period will be equal to 2 pi by omega, which comes out to be 2 pi under root of r divided by g. Okay? And if you calculate the value of this, that is exactly 84.3 minutes. Hence, we are done with the time period of this particle.
Okay, so since we calculated this, it means that if I drop a particle, say from the North Pole, say Arctic Circle, and somehow by geography we know that this has to be the Antarctica. So if I drop a particle from here to here, it will take me around 84.3 minutes to reach from here to here, or to complete one cycle and back. Okay, so
from North Pole to South Pole, it will take like 42 minutes.
Okay, so doesn't it become a little magical if I say that, for example, see, I'm going from, if I'm geographically speaking, if I have to go from Arctic Circle to Antarctic Circle, I will take the fastest mode of transport, which is an aircraft. So does that mean an aircraft, generally speaking, an aircraft will take me, let's go with the minimum figure, it will take me 1 or 2 days from North Pole to South Pole. Does it mean that if I dug a tunnel, which is let's say hypothetical, if I dug a tunnel, does it mean that I will be traveling to the South Pole from North Pole with the fastest means? That means I will be taking only, in fact, half of this, because time period, it will be around 44 something.
So the time taken by the particle to go from the North Pole to the South Pole will be very minimum, and that's simply 42 minutes.
Okay, does it apply? So if we dig a tunnel across, say horizontally along the equator, will the time period be same?
Exactly, it will be same.
Okay.
If you draw any diameter, or for that matter any chord, you'll draw any chord like this. Suppose that this any chord.
Okay.
And you throw a particle here. Okay, this particle is here. This particle is again going to execute simple harmonic motion back and forth, and the time period is going to remain same, which is 84.3 minutes exactly.
Okay.
So from one point to another point on the surface of Earth, you can reach in the minimum time, which is 42 minutes. From here to here, 42 minutes, and the time period will be 84 minutes.
Exactly. Since we are done with the mathematical part of it, but for the love of those who study physics, this equation is. We sometimes, people from physics tend to call this as a magical equation. This T is equal to 2 pi under root of R by G. There are other facets associated with it.
Exactly.
So if you can just put them across.
Okay, so this equation exactly, it's a beautiful equation. And you know what? There's a phrase that is nature loves symmetry. And this equation is repeated so many times in the physics. Okay? Number one is that, if for example, assume that there is a satellite which is revolving around the Earth but very close to the Earth. What's its time period? 2 pi under root of R by G.
Okay.
Number one. Number second is that imagine a situation like this. Earth is spinning about its axis. Now, for example, the Earth spins faster. When it spins faster, the acceleration due to gravity, its value decreases.
Exactly.
If suppose that Earth spins
the centrifugal force.
Earth spins faster such that the time period becomes 2 pi under root of R by G. There will be weightlessness at the equator.
Weightlessness.
Okay.
Exactly.
Number two. Number three. One more. This fascinating thing about this is that the time period of a simple pendulum of infinite length, when its length becomes infinite. Okay. Very very large compared to the radius of Earth. Time period of that is also equal to 2 pi under root of R by G. So this beautiful number, so many times, this magical number, so many times it is repeated in the physics.
Okay. If you generalize this, I must say that this is just not the time period. It is a magical facet. It has many other aspects associated with it, and for the love of physics, for all those people who are watching us, or for all those people who are working out physics at home, they may try all these three things which Sir has actually highlighted. The weightlessness condition, which is the most interesting by far. So this is what actually makes physics beautiful. If you understand it, it becomes a beautiful science.
It is tasty like anything else. Okay, so see you next time. Me and Mohsin sir waiting for you. So take care.
Thank you very much, sir.